Okay, so welcome back to another class of this GATE sessions from NPTEL. Um, so last class we were just starting with mechanical operations. So what we did, we basically went to the basics of characterization of particle, which could be based on the size and shape of the particle. And when we talked about the shape, we went through the basics of a term called sphericity. And when it came to the size, we went through the basic definitions of various different kinds of diameters, mass mean diameter, volume diameter, Sauter mean diameter, and so on. And yeah, and then we briefly went into some portion of size reduction equipment. And just gave a brief introduction with equipments like jaw crusher, fluidized mill, and so on. So today what we'll be doing is we'll continue with these size reduction equipments. So we'll learn a few specific things with regards to things like roll crusher, ball mills, and so on. And we'll also look into the size reduction laws. So there are three different kinds of size reduction laws, and those are, Kick's law, Bond's law, and Rittinger's law. So yeah, so let's get started with this. So yeah, we'll start with the roll crusher. So roll crusher, as the name suggests, it's a type of crushing, equipment, which means the basic principle of a roll crusher is compression. So compression is the basic principle of a roll crusher. And yeah, I'll just briefly draw a sketch of it. So basically, you have two rolls like this, which rotate in the, uh, you know, yeah. So we have two, rolls which will be rotating at, let's say, some pace. And let's say this is our feed particle. So because these rollers are having some, you know, pressure, which is basically the compression that acts on this feed, this will break down, and it will form different particles like this, and it will come down through this roll crusher. So usually you can feed roll crushers with a feed ranging from zero point 0.3 to 0.5 inch feed. And on the outcome you can get products which are even very small in the range of 20 mesh size. So this mesh size, we'll learn what a mesh size means, what the number of that mesh number means, and so on in the next few slides. But yeah, this means basically, it is a very small product, or the size of your product is very small. So that is the thing of roll crusher. And some of these uses of roll crusher is, you can use it to crush oil seeds and even gunpowder. So these are some of the places where roll crushers are used. And typically you can have a feeding range between 3 to 120 ton per hour is the feeding range. So this is just some basic specification with regards to the roll crusher. Now there is something we should know about this roll crusher, and that is something called as an angle of nip. So we'll see what that is. So as we saw earlier, so this, let us say these are our two rolls, and let these be the centers O and B, and let us have a particle like this with a equivalent radius R. Okay, and let me just change the color of this pen. Okay, yeah. So let this distance be 2D. Now if you join the center of this feed particle and the centers of the roll crusher, you will get an angle alpha, and that angle is basically called as angle of nip. No, sorry, it's not. It's actually half of the angle of the nip, and the angle of the nip will be like this. So this angle will become 2 alpha, and this 2 alpha is called as the angle of nip. Now angle of nip, to find this angle of nip, you can have a relation like this: cos alpha is equal to R plus D by R plus R, where D, so 2D is the difference between the centers of these two rollers. So what will that mean? That means half of D is the maximum radius of the feed, right? Yeah, and R is the radius of the feed that you are feeding, and this D can also mean half this distance between, half the distance between the two rollers. So it can also mean that. And capital R is the radius of your feed that you're feeding, and the small r is the this radius distance between center of the roller to the center of the feed. So this distance basically is r. Yeah, and you get a relation like this: cos alpha is equal to r plus d by r plus r, which is basically the principle of adjacent side by hypotenuse. and where alpha or 2 alpha is called as the angle of nip. Now, one more thing that we can um, have a relationship for this is something called as theoretical capacity of a roll crusher. So a theoretical capacity, you can define it as theta in tons per hour, that is equal to 4.352 into 10 raised to minus 7 into n into d into w into small d into s. So this is another relationship that you can use to find the theoretical capacity of the roller crusher in terms of tons per hour. Okay, one mistake is there here. So, okay. So yeah, so that is the theoretical capacity of a roll crusher, and in this formula, N is the RPM of the roller, D is the diameter of the roller, W is the width of the roller, and small d, this is the product radius, the radius of the product that you are getting, and S is the specific gravity, of the feed. So this is just another extra relation that you can use for theoretical capacity of roll crusher, right? So yeah, so that is the these are the things, the basic things with regards to roll crushers. Then there is the next equipment, which is the ball mill. So I'll draw a cross section of this. So this is the side view or cross section view of the ball mill. So you have a huge cylindrical vessel, and inside this vessel you will have small balls. And what happens is, this ball mill, the outside cylindrical vessel, will rotate, and this will take this ball here, and it will go up to this point, and then it will fall back. Now what this does is, when this falls back down to the bottom part, you have your feed also inside like this, and all these feeds will be sandwiched between these balls and will get crushed between these balls, and that is how size reduction occurs in a ball mill. So the main force or principle of size reduction in ball mill is impact, right? And usually the feed size of a ball mill ranges in the range of 50 millimeter, or basically 5 centimeter feedstock, and you can reduce the size to a product size of as small as 200 mesh. So as the mesh number increases, the size decreases. That is the concept with mesh number. I will look into that also after this. But anyways, this means the product is very 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 small. Yeah, right. So one of the most common relation that you can use for ball mill is something called as critical speed. You denote it using the term NC. So let us assume the radius of this mill as r and the radius of this ball as small r. So r is the radius of the ball mill and small r is the radius of the ball. So the critical speed of ball mill can be defined as 1 by 2 pi root of G by R minus R RPS. That means rotation per second. So here G is the gravitational force or gravity. And this NC that you get by calculating using this equation will be in rotations per second. And how we arrived at this equation? It is by force balance. We'll do this exact force balance in detail using one of the previous year gate questions. But yeah, using the force balance, that gravitational force is equal to centrifugal force. So we use this concept and we can derive the equation for the critical speed of a ball mill. So usually a ball mill operates at 0.5 to 0.75 of your critical speed. Now we have been doing all these equations and everything for critical speed, but what is this critical speed? Kind of missed on that definition. So a critical speed, so let's take a ball mill and let's take a ball like this, and let us assume this ball mill rotates as at the critical speed. So at critical speed, what happens is this ball, instead of going here and falling down, it will just keep rotating. So instead of falling down, this ball will also start rotating with your ball. That means it gets carried over by your ball mill because of the centrifugal force that occurs inside the ball mill. So this speed is called as critical speed of the ball mill. And if you operate a ball mill at its critical speed, all your balls and particles will just keep rotating with your ball mill, and no crushing or size reduction will happen. And that is the reason why we usually operate your ball mill at 50 to 75% of your critical speed, so that the ball from here goes here and then it falls back down and crushing happens, and your size reduction also happens. So that is the definition of the critical speed of a ball mill. Right. So yeah, so this is just some extra details with regards to some of the size reduction equipments that are normally being used across the industries. And as I said, we want to look into something called as mesh size. So before we go into this mesh size, our next process, so we looked at size reduction, and the next process that we'll be looking is called as screening. So you must have seen this screening in a lot of places, where you screen, for example, construction workers, they screen the sand that they are using a screener to separate out the particles based on their size. So that is basically what screening is. Screening is the separation of particles based on their size, right? So one of the most used lab equipment for screening is something called as a sieving machine, or it is also called a sieve. So what a sieve is, so it's basically a plate that has a lot of interlinked wires. So this is basically called as a sieve. This plate is called as a sieve. And this arrangement is called as a mesh because it's arranged, in a cross pattern. And what happens is if you have a particle and let's say this mesh opening has a size of, some 1 centimeter square or something. Let's say that is the area of this mesh opening. If your particle is greater than 1 centimeter square, it will be retained above the mesh. And if it is less than, this mesh opening or the 1 centimeter square, it is passed down through the mesh. And that is how separation of the particles happen using a sieve or a mesh. Now, the next thing is the mesh number or the mesh size. So what this means is, for example, if you have something called as 20 mesh size. So this means there are 20 opening per square inch in the sieve. So each opening is like this, and there are 20 such openings like this in 1 square inch area. That is called as 20 mesh. So that means if it is 200 mesh size, this will have 200 openings per square inch of the sieve. So that is what is called as a mesh size. And usually the difference between two mesh sizes are based on Taylor series. So you have a mesh like this on the top and other mesh like this on the bottom. Yeah. So let's say the area of this opening is A1 and the area of this opening is A2. Now, because these meshes are, basically square in shape, this A1 can be basically L1 square, where L1 is the length of the, mesh that or the opening. And let's say L2 is the length of the opening here in A2. So A2 will be L2 square. Now, the concept is that the mesh sizes are arranged according to Taylor series. That means this A2 will be equal to 2 into A1, or the area. Okay, A1 is on top, so it should be A1 should be higher than A2. So area on the top A1 is twice that area of the bottom mesh, that is A2. So A1 is equal to 2 into A2, or you can write L1 square is equal to 2 into L2 square. So if you take the ratio L1 by L2, that will be equal to root 2. So this will be the ratio of the lengths of mesh of adjacent mesh in a sieve. So this is just some extra data that you can note down if you want. But yeah, so that is how usually meshes are designed, across. Okay, so fine. So let's stop the theory part here, and we'll try to solve some previous year gate questions. If there are no doubts, we can move to the gate questions. Um, I'll wait for a couple of minutes, and if anyone has any doubt, please do type or speak up. If there are no doubts, we can start, with the questions. Fine then. Let's get on with the previous year questions. So this is a question from GATE 2013 from Chemical Engineering, question number 14. In the Tyler Standard Screen Scale series, when the mesh number increases from 3 mesh to 10 mesh, then option A, the clear opening decreases, option B, the clear opening increases, option C, the clear opening is unchanged, option D, the wire diameter increases. So this is a question from screening part of mass transfer operations, and the reference NPTEL lecture can be found in Unit 1, Lecture 4, Characterization of Collection of Particles 1, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here they have mentioned about a Taylor mesh, or a Taylor standard screen, or a Taylor mesh screen. So a typical mesh screen will look like this. So it is basically a plate having wires crossed from right angles. So this is typically how a mesh looks like. And when they say a clear opening, these are the clear opening of a mesh. So the question here is, when the mesh size is increased from 3 mesh to 10 mesh, what happens to the clear opening, or will it remain unchanged, or will it affect the diameter of these wires that are used for crossing the mesh? So before we proceed, one more thing we need to know is that the mesh number. So when we say 3 mesh, that means there are 3 clear opening per square inch of the sieve or the mesh screen. And when we say 10 mesh, that means there are 10 clear openings per square inch of the mesh. So clearly you can say, so a rough pictorial representation would be like this. So if this is a square inch and there are 3 openings, and this is a 3 mesh, and if you represent the same using a 10 mesh, so let us say 3 4 5, 1 2 3 4 5. So let us say this area is 1 square inch and there are 10 openings for a 10 mesh. So clearly what you can see here is that when we are looking at the 10 mesh, the opening or the size of the opening decreased in the 10 mesh size. So clearly this indicates that as the mesh number increases, the number of clear opening increases, and that means the size of the clear opening decreases. So looking at the options that we are given in this question, option A is the only option that mentions that the clear opening decreases or the area of the clear opening decreases. So here the right option is option A, the clear opening decreases. So when the mesh number is increased from 3 to 10, the clear opening decreases. Yeah. Okay. Yeah. So just recap this question by yourself. We'll and if there are any doubts, just ask me. Okay. Fine. If there are no doubts, we can proceed with the next question. Yeah. Hmm. Yeah, even that is what I am also trying to check with the answer key. So this can have two meanings. Either the area of the clear opening decreases or the number of clear opening increases. So let me just check the answer key and see what they have said. In the meantime, if you guys can also search for some answer keys for this GATE 2013 question, just do it on the side and we'll check it side by side. Okay, so the clear opening decreases. That is, yeah. So yeah, I think this is right only. So what they have tried to say is the clear opening is basically the area of the opening is what they are trying to imply here, I think. So the answer key also says the option is A. But yeah, this if they mentioned number of clear opening decreases or increases, it's definitely option B, because the as the mesh size increases, the number of clear openings increases. But here, I think they have meant it as the area of the clear opening, or basically clear opening means they are trying to mean it as the area of the opening. So because of that, the clear opening here decreases when the mesh size moves from 3 to 10. But yeah, the other way is also right if they have mentioned the number of openings. So that is a good observation. Yes. Fine. Is there any doubts, or shall we just move on to the next question? Okay, if there are no doubts, we'll move on to the next question. Right. So this is a question from chemical engineering from GATE 2010, question number 1. The critical speed or revolutions per unit time of a ball mill of radius r, which uses balls of radius small r, is, and the four options are given as the follows. So this is a question from size reduction equipments, and the reference NPTEL lecture can be found in Unit 3, Lecture 15, Size Reduction Equipment 2, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So, by definition, critical radius, which is also represented as NC, is the speed at which the balls of radius r gets carried over or carried around by the rotation of the ball mill, which has a radius capital R. So if this is the cross section of the ball mill and if this is our ball at critical radius, instead of going here and falling down, the ball will just keep rotating along with the ball mill. And if this occurs, then there is no impact and then there is no size reduction also. So that is the critical speed of a ball mill. Now, At critical speed, there are two forces that come in equilibrium. One is the gravitational force and the other is the centrifugal force. And at critical speed, this gravitational force will become equal to the centrifugal force. Or we can write mg is equal to m into r into omega square. Now this r, you can't directly take it as a small r because this is basically the effective radius. And here we have to take this effective radius as the difference between the radius of the ball mill and the radius of the ball. And omega square is basically the angular velocity and m is the mass. So by using this force balance, we can derive an equation for the critical speed. So again writing mg will be equal to m into r effective, which will be the difference between the ball mill and the ball radius into omega square. And here both the m will get cancelled and g is equal to r minus r into omega square. So the angular velocity omega can be written as 2 pi into n. And here it is, since we are mentioning it as critical speed, we can write omega is equal to 2 pi into nc, where nc is the critical speed. So omega square will be 2 pi into nc the whole square. So 2 pi nc the whole square into r minus r will be equal to g. Or if we rearrange it, 2 pi nc the whole square is equal to g by r minus r. Or 2 pi nc is equal to root of g by r minus r. Just one more rearrangement, we can write nc is equal to 1 by 2 pi root of g by r minus r. And this will be the equation for the critical speed of a ball mill. And in the various options given in the question, option D satisfies this equation. So that means for this question, the critical radius or critical speed of a ball mill is given by the option D, which is 1 by 2 pi into root of g by r minus r. Right. So I hope this was understandable. So basically what we did was just we took the force balance between gravitational force and centrifugal force because these two forces will be equal at critical speed, and we just using this force balance we just derived the equation for the critical speed, which comes out to be 1 by 2 pi root of g by r minus r. Right. Okay. So yeah, if there are no doubts, we'll solve one more question. I think we have time for one more question. So we'll solve one more and see what happens. So if there are no doubts, we'll move on to the next question. This is a question from chemical engineering from GATE 2013, question number 34. 100 ton per hour of a rock feed of which 80% pass through a mesh size of 2.54 millimeter were reduced in size such that 80% of the crushed product passed through a mesh size of 1.27 millimeter. The power consumption was 100 kilowatts. If 100 ton per hour of the same material is similarly crushed from a mesh size of 5.08 mm to a mesh size of 2.54 mm, the power consumption in kilowatt to the nearest integer using Bohn's law is dash. So this is a question from size reduction laws in mass transfer in mechanical operations, and the NPTEL lectures can be found in Unit 3, Lecture 14, Laws of Communication to Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here they are following Bohn's law for size reduction. And by Bohn's law, the equation for Bohn's law is P by m dot is equal to K into 1 by root of dB minus 1 by root of dA, where P is the power consumed, m dot is the feed rate in tons per hour, dB and dA are the dia of the feed and product. And K is the constant, the Bohn's law constant. So let us write down all the data that they have given in this question. So in the first part of the question, they have given the sizes 2.54 millimeter was reduced to a size of 1.27 millimeter. So we will write the Bohn's law for this size reduction first. So let's take it as 1. The diameter dA is given as 2.54 mm. dB is given as 1.27 mm. The power consumed P is given as 100 kilowatt, and the mass feed rate m dot is given as 100 ton per hour. Now we just write the Bohn's law again. The Bohn's law states that P by m dot is equal to K into 1 by root of dB minus 1 by root of dA. And here we have all the values except for this constant K. So what we need to do here is substitute all these values here and find the constant K. So substituting all these values, we can write 100 by 100 is equal to K into 1 by root of 1.27 minus 1 by root of 2.54. And solving this equation, we can get the constant K is equal to 3.8476. Now all we have to do is use this value for the constant K in the second size reduction that they have asked us to find, which is the size reduction from 5.08 mm to 2.54 mm. So now we have the value for K, which is 3.8476, and in the second case dA is 2.54 mm and dB is 5.08 mm, and the power P is the unknown here, and the mass flow rate m dot is given as 100 ton per hour. So now in the second case, since we found out the constant K from the last case, using that constant and using these new diameters of the feed and the product as well as the mass flow rate, we need to find the power consumed. So again we use the same Bond's law. P by m dot is equal to K into 1 by root of dB minus 1 by root of dA. So we'll substitute all the values that we have. P by 100 is equal to K, which is 3.8476 into 1 by root of dB, which is given in the question, 1 by root of 5.08. And if we solve for this P, we can get the power consumed. P is equal to 70.71 kilowatt. So the right answer here, which is the power consumed for this size reduction, is 70.71 kilowatt. And to the nearest integer, this will approximately become 71 kilowatt. Right. So basically in this question, what happened is they have given us two different size reduction processes, but both these size reductions are following the Bond's law. So using the case 1, we had all the data there except for the Bond's law constant, which is K. So we used those data and found out the constant K from the case 1. And then from this, using this constant K, we supplied this constant K to the case 2, and using those values given for the next case, we found out the power consumed for the second case, and that came out to be 70.71 kilowatt, and which is roughly equal to 71 kilowatt power. Right. Any doubts with regards to these three questions that we solved? Please, you can always ask or chat. And yeah, if there are no doubts, then I guess we'll stop here for today. So in the next, so this class we just gave a brief introduction to screening. So next class we'll look into something called as the effectiveness of screening, and we'll look into some detailed equations with regards to screening and sieving, and we, if time permits, we'll also look into settling of a particle. right? So yeah, that's it for today's class for mechanical operations. And yeah, as I said, if you have any doubts, you can always ask the questions. If you are able to, if you're unable to solve any previous year gate questions and you want me to discuss those questions, you can always email me those questions as well, and we can try look into it in the subsequent classes. So yeah, so that's it, and I guess thank you for joining. So before you guys leave, like, can someone say when is the gate exam for chemical? At what date is the chemical engineering exam? Anyone know? Right. Okay. So 11th Feb. Okay. So we'll mostly have these classes of mechanical operations till the gate exam happens. So I guess that gives us some 4 to 5 classes, and hopefully that should be enough to finish all the portions with regards to mechanical operations. Yeah, then I guess fine. Then I'll see you all next Monday, 6 o'clock. Yeah, thank you.